All right, so now we're looking at FRQ set number 2 for the 2024 AP Physics C Mechanics exam. If there are any corrections, I will put as a pinned comment, and you guys will point out anything that I did wrong. So let's go. Blocks A and B of masses 2m and m respectively are arranged in a setup consisting of a ramp that makes an angle theta. With the smooth horizontal table and an ideal spring of spring constant K fixed to a wall as shown, block A is held at rest, the distance d up the ramp. Block B is at rest in the horizontal table. The coefficient of kinetic friction between block A and the rough ramp is mu, right here. And there's negligible friction between the blocks in the smooth table. So a little bit similar, a little bit different because of the inclined plane, but similar to set 1. Okay, so, I don't want to assume this. So this is T1 is we get down the ramp and is moving at speed v here. And then at T2, it's at x2 where it collides and sticks. And then T3 is the combined blocks A and B are stuck together and the spring is compressed a distance. Derive an expression for the V at block A at times T1. Okay, so here the system's going to be gravitation, the Earth and the block. Gravitational potential energy. The energy we have here is gravitational potential energy. Down here we have kinetic energy, and we're going to do some work due to friction. Now, how much are we going to do? We're going to have external work done, right? Because we have 2mg, we have normal force, and then we're going to have some friction here. And so we are going to lose some energy due to friction. There's going to be some work being done here, right? So energy is not conserved during this motion. Here's the displacement. Friction's going to do negative work. So again, for this one, I always think about work is the change in energy. Now the work is negative mu Fn times d, and then we'll get to the Fn here, and the change in energy is the 1/2 mv squared minus, that's the energy we have down here, and initially we have gravitational potential energy because we included Earth in the system, so we're not going to have the 2mg doing any work, right, because that's internal, but instead we account for that by the gravitational potential energy, which is mgh. Now what is the height here? The height has to be in some of these things, so here's h, and so this is, because the d is the hypotenuse, and this is theta, this has got to be d sine theta, right? Minus mgh. Now the normal force, because in the y direction is not accelerating, the normal force is going to equal 2mg, that's theta, 2mg cosine theta, right? That's the normal force there. So then this is going to be negative mu 2mg cosine theta times d equals 1/2. This is 2m v squared minus 2m g d sine theta. Now the 2m, I can drop the 2m's because the mass actually did not matter there. And then I'm going to add this over. So we're going to have gd sine theta minus mu g cosine theta times d is equal to 1/2 v squared. So we just double that and then square root it. Okay, so hopefully I make that relatively legible. Okay, so then it collides, so we have to do conservation of momentum. We have a 2m moving at v, and then we'll call this v2, and then we want to know the max compression. So v2 is after the collision, and then we'll convert the kinetic energy into spring potential energy, right? That's kind of the idea. So we're going to say the initial momentum is 2m v. The final momentum is because they have a combined mass of 3m, so it's going to be 3m times v2. And so you're going to set those equal to each other by conservation of momentum because there's no external horizontal forces. So the m's cancel, so you get v2 is equal to 2/3 v, where this is v, and we'll just plug that in later. And then we're going to use conservation of energy. We're going to say, well, 1/2 3m v2 squared. That's how much kinetic energy we have. That's going to get converted into spring potential energy. And how much did we compress the spring? xc here. Okay, xc squared. And we want to solve for the spring constant. So the 1/2's cancel, and we can move the xc over. So we're going to have k is equal to xc squared, 3m v2 squared over xc squared, where v2 is 2/3 of this thing. So when you square it, it's 4/9. of this thing without the square root times 2. I'm going to pull out the GD, and then I get sine theta minus mu cosine theta. Okay, over xc squared. I don't know. You want to simplify that? I guess we can simplify this. This is 3. 4 times 2 is 8. So I get, what, 8 thirds mgd sine theta minus mu cosine theta over xc squared. Okay. I think that's right. If I made an arithmetic mistake, entirely possible. I'm prone to do that. Okay. On the following sketch, a graph of the magnitude of the momentum PA of block A as a function of time. So set 1, they actually asked for it was a little bit different. They asked for the energy, but they want the momentum as a function of time. So this one is integral of f dt is the change in momentum, right? So we want to think about whether there's any external impulses on this thing. And the momentum is just equal to m times the speed, right? The velocity. And they want the magnitudes. They don't care about the fact that there's an x and a y component. They just want the total magnitude. Well, initially what's happening is there's a constant force. He's just accelerating. So his speed is going to go up linear. His velocity increases linearly, so the momentum will increase linearly as well. Okay? Then the momentum stays. So this is just the momentum of block A, by the way. So now the momentum is going along to T2. Then it hits this thing. Now be careful. When we say momentum is conserved, we definitely say the total momentum is conserved. But if we're just talking about block A, he's definitely going to slow down, right? Definitely slows down. So and technically he's going to slow down by 2/3 of the original speed he went. So he's going to drop by a factor there. I don't think you need to be that accurate, but it just have to drop by some there. And then the spring force exerts on it, and it brings it to a stop. So his velocity comes to a stop. Now, the force that we're doing, so the question is we're definitely going to 0. But the tricky part is, what is the shape of this? Okay? So we're integrating over time. Okay? And what's happening is, if you think of, so there's a couple ways to think about this. So one way to think about it is, if you think of the velocity, like if it sticks to the spring, it would just oscillate back and forth. So in that instance, what would the velocity look like? It looks like a sine curve or a cosine curve, right? The velocity would start 0, and if I'm plotting v of t, and the velocity would be like a kind of a sine curve. It would oscillate like this, right? So initially it would have a 0 velocity. Actually, no, it would start here with a lot of velocity and then come to eventually to a 0 velocity, right? That's this is the equilibrium position this is the equilibrium position where the velocity is maximum, right here. And then we compress it down to here. So it's going to have this concave down kind of relationship. Like it's going to go down. It's like going to be part of a sine curve, right? And it's going to be steepest right at that point there. Okay, so it's going to have a little bit of a curve because it's that portion of that sine curve if it were oscillating. Use principle of forces to justify your answer in graph of part B. Okay, so in terms of forces, well, so in from T3 to T4, so they're asking about this part. They're asking in terms of forces, why does the momentum look like that, right? Well, so the force from the spring is equal to m, dv dt, or ma, right? And so initially, the spring force is 0, which implies the dv dt is 0, which implies the horizontal tangent line, right? Like right there. It's a horizontal tangent. Okay. As the spring force increases, increases with compression, the acceleration increases in the negative direction. Because it's pushing this way to the left, right? And all of this we assumed, when I used positive numbers, I assumed right was positive. In the negative direction, so it gets steeper, which is what you see here, steeper. Okay, cool. For times t greater than t4, the two-block system oscillates with a period t0. The procedure is repeated using a new ramp where there's negligible friction between block A and the ramp. Indicate the new period of the oscillation is used. The period is 2 pi root m over k. And actually, in this case, because in terms of the variables, it's going to be 3m because it's a 3m block. But it doesn't really matter. The mass and the spring constant, but the masses and spring constant are unchanged, which means the period doesn't change. Okay, that's question 1. Question 2, a student drops a sphere of mass m from rest. The air exerts a drag force of magnitude F drag on the sphere, as F drag equals BV. Derive but do not solve a differential equation that we can use to determine the speed V as a function of time. Okay, so we start with drawing a free body diagram. That's always the first step I teach my students. Any one of my students that didn't draw that free body diagram, then they get this. Okay, so we have drag force upwards. They pointed it upwards, and you have mg, and there's nothing else touching it, so that's it. What's the next step? Next step is, what is the acceleration? Well, you dropped it from rest, so it's going to accelerate downward initially. And so we'll make down the positive direction, and then we do F net equals ma, which means mg minus bv equals m, and then the a is simply dv dt. And that is a differential equation for v. You don't have to solve that, though. Student sketches the drag force exerted on the sphere as a function of time. Draw a vertical line on the sketch to indicate the earliest time at which F drag is equal to the magnitude of the weight of the sphere. That is where the two forces are equal, so the net force is 0, so the acceleration is 0, and that's going to occur right here. So that is what do they call it? TT. Okay, and that is because the net force is 0 there, which implies A is 0, which implies the slope. Oh, wait, this is drag force. This is not velocity. I want to double check something on the. Okay, the last set had them do velocity. That's why I was doing velocity. Okay, so the F drag, when the sphere reaches its terminal speed. Okay, so I would normally say it's the slope, but it's not exactly the slope. We want the net force to equal 0 at the terminal speed. Okay, so at terminal speed. And then what that means is the drag force, right? That's when it equals mg. And trying to think of what feature of the graph that I cares about it. Do I care about the slope? The derivative of that's not really the. So the F drag is equal to BV. When we reach terminal velocity, the F drag isn't changing anymore. Well, okay, so I guess like when F drag, so at terminal speed, there's no change in velocity. So there's no change in, because the V is constant at terminal velocity. So once it gets there, so there's no change in the F drag because F drag equals BV, which means that's where F drag is a constant. Okay. Or slope 0. Right? The drag force is not increasing anymore. You're not going any faster at that point. Okay. Suppose the student throws the same sphere downward with a non-zero initial speed. The magnitude of the new drag force at terminal speed after being thrown downward is F new. Indicate whether F new would be greater than. Well, F new, the F drag, sorry, is equal to at terminal velocity. At terminal speed. Is when BV is equal to mg. So we know the V terminal is equal to mg over b. So the terminal speed doesn't change because the same mass, same g, same b coefficient. That's a constant. So we assume that Vt is the same, and that implies that because F drag equals b, I just say that like it's equal to the drag force is equal to mg, right? At terminal speed, it's equal to the mg. So it doesn't really matter. Yeah, just F drag equals mg. The mass doesn't change, so it's equal to, right? Okay, student conducts an experiment and does F drag versus V. So he does, draws a line. I don't know, just Fine, that's my line, okay? With this straight edge, you can make something a little bit better. Draw the best fit line, use the best experimental value for B. So F drag is equal to BV, right? So this is our Y value. This is our X variable. So what's our slope? Our slope is equal to B. So we're just going to read off 2 points on here. We'll pick off this point here. This point, oops, let me pick a different color. We'll circle this point right here. This is the point 1, 2, 3, 4, 5. So each of these is 1. So this is 3, comma 1, 2, 3. Each of these is 1 also. 1, 3, comma 3. And then we'll pick this point right here, which is, I don't know, 21, 2, 3, 23, comma 15, 16, 17. Right? And so that's going to be 17 minus 3 over 23 minus 3. I'll just use the calculator for that. That's going to be 14 divided by 20. It's going to be 0.7. And what are the units? Well, they give you newtons, meters per second, newtons over meters per second. So just call it like that. Okay, student claims that the terminal speed of the sphere depends on the diameter. The student designs an experiment to collect data that can be used to provide evidence to support the claim. So we have a set of spheres of the known mass with different known diameters, or spheres with the same known diameter and different known masses. Motion detector can measure velocity as a function of time. Indicate 2 quantities when the graph could be used to determine whether the diameter of the sphere affects the terminal speed. So we want the terminal velocity, okay, because we're going to use the motion detector. And then the horizontal axis, we want to use the diameters. And this is just simply saying, if we don't know if this is linear or not, so you just need to say if it's going upwards or not. If there is an upward or downward trend, then there is a relationship. And if there is a horizontal line and trend, then there is no relationship. Hopefully you guys have better handwriting than me, okay, when you guys take these tests. All right, number 3. Interesting. Non-uniform disk of radius r and mass md is attached to a vertical pole by a horizontal axle. It passes through the center of the disk. So this is the horizontal axle here. Uniform disk. Interesting. So it's like spinning this way. Okay, interesting. Friction between the axle and the disk is negligible. A lump of clay of mass mc is attached to the edge of the disk at point A. The size of the lump of clay is small compared to the radius of the disk, so you don't really have to care about the dimension of it. It's like a point mass. A horizontal string is connected from the pole to the edge. The string makes an angle theta with the line between point A and the axle. On the following representation of the clay disk system, draw and label the external forces, not components, exerted on the system. Each force must be represented by a distinct arrow. Okay, so they want you to draw all the forces. So we have the clay disk system. So I'm going to start with the gravity. I got gravity of the disk. We'll say Fg of the disk. Here we'll have the gravity of the clay. Then what's touching it? Well, they're touching each other, so we don't have to worry about that because they're part of the system. We have a string here, so there's a tension right at this point. And then the axle might exert a force because it's just sitting there. I think we assume that it's just hanging out here. The axle has to compensate both for the downward and leftward force. Otherwise, this disc would like accelerate to the left or downward. So we'll say upward. This is F from the axle. Okay, and I think that is good. Derive an expression for the tension in the string when the clay is at point A, as shown in figure 1, in terms of R, M, D. Okay, so we want to first identify axis of rotation, which is right here. Right, because that will eliminate those 2 forces when I do net torque equals I alpha. And then we're going to draw, and then what is theta, by the way? Theta is this angle here. So I'm going to draw an R vector from here to where the forces are applied. We're going to say this way is counterclockwise. This is the positive direction. This is the negative direction for the torque. So that is the angle R. Now, they're saying this angle is theta, which means on this axis, this angle is theta. So we can decompose R into 2 components, right? because we gotta take components perpendicular. So this is going to be r cosine theta and r sine theta. And these are the only two forces exerting torque, because these act at r equals 0, so they don't exert a torque. So we're using the net torque is 0. So that means the torque from this guy equals the torque from this guy, or the sum of the torques are 0. Now, the torque for the tension, we care about not r cosine theta, we care about r sine theta, because that's the one that's perpendicular to the tension, the upward component of that vector there. So we would say r sine theta times the tension, I guess call it ft. We'll label it ft. That's just an extra letter I have to write every time. But I will write the ft, and that's to equal the torque from this guy, and that's where we use the r cosine theta, because the force of gravity of the clay is perpendicular to r cosine theta. So r cosine theta times mass of the clay times g. So the r's cancel, and you get the tension is equal to mcg cosine theta over sine theta. Make sure you do like the net torque equals 0 and show all of that kind of stuff there, even if you didn't quite get this correct. Okay, the string remains connected to the edge of the disc at point A. The clay is moved to point B, which is horizontal line, as shown. How does the new tension compare with the tension? Justify your reasoning. Well, so now there's a couple things that are happening. We are now increasing. So this is mcg. Okay, so now the r and then the tension is this way. Now it's just going to be, this is r. But notice that again the net torque has to be 0. So we still have this, but now the r is perpendicular to mcg, so that's that one torque. This tension is going to have to be really, really huge, because you notice that it doesn't exert any torque on the system in terms of this rotating part. So it actually can't keep it from rotating, the tension alone. The tension is just going to have to, it's going to have to be really high, because it's a horizontal line, but think of it this way. If there was a slight angle there, then the tension would have to be huge. Ultimately, this thing is going to start rotating. The tension is not going to keep it up here. So it's going to be larger. The ft nu has to almost be infinite, because the r is almost is basically parallel to the force, parallel to ft, which implies the torque is almost 0. So to keep the net torque equal to 0, ft would have to be huge. In fact, if it was totally horizontal, it's impossible. What would happen is that it would go down a little bit, right? It would swing a little bit here, and then once there was an angle, then there would be some torque to balance that out. But it would have to swing a little bit. It would be really impossible to keep it totally horizontal there, because technically it could not exert a torque at all. And so then it would rotate a little bit, but then the tension would probably be enough to keep it stopping. But it would be very, very big at that point, much bigger than whatever it had to be up here. Okay, non-uniform disc is attached to the axle. The lump of clay is attached to the disc at point B. As shown in the figure, the clay is a mass mc of 0.6, and the disc is a radius 0.3. The mass density of the disc varies radially and can be modeled by this equation, where r is the radial distance from the axle. Calculate the rotational inertia of the disc about the axle. Okay, so the rotational inertia is the integral of r squared dm. Now, what they're telling you is the mass density of the disk can be modeled where r is the, so I think they just want you to do r squared times the density. I don't like times dr. This is a little bit tricky. Yeah, I think that's what we're gonna have to assume. That it looks like this. It's not super clear. They're saying the mass density of the disk varies radially. So I honestly wish they would tell you if it was like an area density. If it was like an area, they don't give you any unit. Oh, actually, sorry, they did give you units. Okay, so this is per. Okay, so this is per meter squared, which means I got to multiply it by an area. So for dm, I have to do the density times some kind of area. Now, what is the area? Well, because it's radial, your area, this is probably one of the trickier integral setups. The only ones harder are doing the rotational inertia for a sphere, but that usually requires you to know multivariable calculus. So it's a thin ring of distance r, and that's the area. I want the area of that ring. Now, the easiest way to think of the area of that ring there is you think of it as if I were to snip it and roll it out like a rectangle, the length of that rectangle would be the circumference of the circle times the thickness, which would be dr. So that is the dA part of that. So then this is going to be, we'll put dA here. This is going to be the integral of r squared times beta r times 2 pi r dr. Okay? And that would then be, and then we're going to integrate this from 0 to capital R. So this is the integral from 0 to capital R, and then this is r to the 4th beta 2 pi r to the 4th dr. And that's going to be 2 pi beta r to the 5th over 5 from 0 to r. And that's going to be 2 pi beta r to the 5th over 5. Okay, and then we just plug in numbers. Beta was 4. 4 times 2 times pi times, what was big R? 0.3. 0.3 to the 5th divided by 5. And I get 0.0122 kilogram meter squared. And let's just double check the units are right. So the beta is kilogram over meter cubes. This is meters to the 5th. So kilogram meter squared. So yeah, I think I did that right. The string connecting to the disk to the pole is cut. Calculate the magnitude of the initial angular acceleration of the clay disk system. Okay, so we cut this string here. So we only have one torque from here. So we use net torque equals I alpha. Okay, and the net torque is just going to be R times mcg, or mc, yeah, the mass of the clay. And the I, be careful, is the 0.0122, but technically mcr squared, because we got the rotational inertia of this thing, because we got to do the clay disk system. This is probably very small, but we'll take a look. So this is, so R times mc times g, so this is 0.3. mc is 0.6, and g is 9.8. This is equal to 1.764. is equal to this 0.0122 plus mc, which is 0.6 times 0.3 squared. Okay, this is 0.0662. So you couldn't neglect that. It wasn't that negligible. And then we're just going to take that 1.764 and divide it by that. And hopefully I did the calculator correctly. I get 26.6 radians per second squared. Like that. And that's it.